drifts along, that does a little bow tie, that drifts along and gets put into the washing machine a little bit, and then drifts along and they're in another storm pattern. The site is really informative. They've got great pictures. I encourage anybody to check in as time goes on. And the drift, of course, started in late September and goes until next year, late September. The other thing I wanted to draw your attention on that's very interagency is the CIDFEX website, which I've brought up right here. And this is a drift track forecast that has international participation. You can see here from UK Met, NRL, Environment Canada, the ESRL model, which is what we run here, ECMWF, University of Washington, AVI, University or UK Met, and METNO. So you can put in different targets, which also include buoy locations, and we'll hear about a bit more about that as well. And then you add in the date, and you can bring up graphs of what the drift forecast is. So, for example, this has been the drift in latitude. It might be the easiest thing to look at. And for the next 10 days, these are what the different models are projecting. And then here it gives you an idea of how the different models are doing. And there's many different ways to visualize this information. And I think it's been a fascinating near real-time model intercomparison study. And if you even go into Browse Forecast Archive, you can see how we've done in comparison to the buoy observations. Okay, so that's what I wanted to say while people are formulating their own updates, and now just put it to the group. So please unmute yourself and provide information.
Hi, this is Jackie. I wanted to alert everyone about the fact that the Arctic Report Card for 2019 will be released at the AGU meeting in San Francisco on the 10th of December, which is a Tuesday at noontime. So if you want to hear what the latest is with regard to the report card, feel free to go to that press release.
Thanks, Jackie. Will you be on the panel presenting? Or will there be a panel?
Yeah, yep, sorry. Yeah, there's going to be a panel. I don't know who's going to be on it, but it will be it's typical kind of format. There'll be a panel of probably 3 to 4 folks that are, contributing to the report card, and then the other authors will be there, and then it will be opened to questions. This year, we're really excited about the fact that we added a new essay that reflects the indigenous perspective, and with a focus on what's going on in the Bering region.
Great, that sounds really great. Anybody else with an update?
Yes, I think just 2 hours before the press release for the Arctic Report Card, there will be a MOSAiC press workshop at AGU, and there will be a panel there to answer questions and present, the latest results.
Thanks, Melinda. Anyone else? Okay, well, if not, then we will go on to our first.
Janet,
yes.
Janet, it's Martin. Sorry, I, of course, was talking to myself on mute. Could I just say a quick word?
Please.
Thanks. On Thursday and Friday this week, the National Geospatial Intelligence Agency, NGA, is holding an Arctic Maritime Domain Awareness Symposium, and there will be an IARPIC presence there. I'm pretty certain that Sarah Bowden will be there. Sandy Starkweather, the co-lead of our IARPC observing team will be there. I will be there. Chris Polashensky of CREL, who I don't think is on this call, he will be there. Chris is a panelist, and I'm the moderator of that panel. Sandy is moderating a panel, and I'm a speaker on that panel. I think there are other IARPC folks there, like Dave Kennedy from NOAA. And this makes sense because NGA is interested in learning more about the research space in the Arctic and where the gaps and needs are and how it could contribute. And I think sea ice is going to be a major topic. So NGA is not an agency that advertises itself a great deal. It's part of the IC. I leave you to look up what that means if you don't already know. But one of our points of contact at NGA is very interested in IARPC, and perhaps we could convince them to do a briefing sometime, maybe a multi-team briefing sometime. Thanks.
Hey, Martin, this is Kathy Wilson. Who would you suggest from the NGA, and do they participate already in IARPC or not?
Not quite, but very interested in doing so, and we're working on that to persuade them to get involved.
I can jump in here too. This is Sarah Bowden from the Secretariat. So Mike Brady is a point of contact, and if you need his contact information, I can get that to you. And they have done some briefings and participated in a few IARPC staff group meetings, but we, as Martin said, they are going to become more involved, particularly in the environmental intelligence area.
And
Great.
Kathy, I would add that Laurie is a member of the panel that I'm moderating at the meeting. So Sandia is already connected.
Got it. And I know Mike, so that's great. Thank you very much, Martin and Sarah.
Okay, thank you for that, Martin. I think we have time for if somebody else would like to provide an update. If not, we'll move on to our first speaker, who is Chris Cox. And I will just bring up his presentation. And I'll let Chris introduce himself.
Hi, everyone. Thanks for having me. My name is Chris Cox with CIRES here in Boulder, Colorado. So I'm sure many of you have heard about the MOSAiC drifting experiments, a multinational drifting expedition. Presently, the Alfred Wegener Institute's PolarTREC icebreaker is moored to an ice floe about 86 north in the Siberian Arctic, and is drifting with the transpolar drift as we speak. This experiment is quite large, and it's actually spatially distributed, some 40 nodes or so in all directions around Polarstern, about 40 kilometers out. So there were actually two ships that went out on the deployment leg. The second ship was Academic Fedorov, a Russian icebreaker. It's actually an ice vessel, not an ice class vessel. It's not really an icebreaker, but you can see the bow of it in the cover slide image here. So I was on that vessel, and that vessel was tasked with deploying the distributed network, what we're calling the distributed network, this array of assets away from Polarstern. And I'm going to give a quick overview of some of the ice conditions that we encountered. It's going to be very qualitative and picture oriented. There was a lot of data collected, of course, but I'm not going to be sharing that. This is an image of the ice analysts, what the ice analysts were using from ARI on late September. And it shows the ship track of Fedorov. So we come out through the Barents into the Kara Sea, and around September 25th or so, we enter this ice tongue that extends somewhat south of the main ice edge, and actually was moving north at the time. And this is so kind of east of Severna Zemlya there, and north of Cape Baranova. Generally, we're following, we kind of cut through that ice tongue and then over to the marginal ice zone on the Laptev side in order to move north towards the main position where you can see all the dates kind of consolidated together. We spent a few weeks up there. That's where the main site is. So we're sticking with kind of the marginal ice zone in order to advance quickly through the ice. But in general, anecdotally, what I'm understanding from the ice scientists that were part of the operational ice crew on Fedorov is that they were actually expecting considerably thicker ice, maybe even twice as thick. Most of the ice that we're passing through is maybe 30 centimeters, 40 centimeters thick at most. We didn't see anything that was older than about 11 months old. So everything was either newly forming ice this autumn or ice that had lasted through the one summer. And of course, the actual ice observations that we're making are probably a little bit biased because we're sticking to the leads in order, again, to maximize the efficiency of travel through on our transit through the ice. This is SAR imagery that shows the black streaks showing some of those leads and the orange track showing where the academic Fedorov was traveling on September 29-30 sort of time frame. The pink outlines show some ice flows that were proposed flows for MOSAiC. I believe it's the top right one on site 3 was the one that was eventually chosen. This was a map that was made operationally during the flow selection period. Site 5 down at the bottom, we actually entered that flow briefly with Fedorov in order to test the conditions within the ice flows themselves. So here's an image from us doing that. So you can see the cracks sort of forming out in front of the ship, and then looking down from a height of 80 to 100 feet or so from the bridge, you can see the ice thickness, generally pretty thin in the 50 centimeter range for this flow. But mostly what we were seeing at that time looked something more like this, these small remnant pieces with a lot of newly forming ice in various stages in between: grease ice, nihilus, finger rafting, so on and so forth. I'll just flip through a few images of that. Every now and again we'd encounter something a little bit thicker, but again, it's still only passed through one summer. This is a particular piece here it's been turned over by the ship. So what you're seeing is the underside of the ice, this rotten ice underneath, which in this case is brown because of algae. We didn't see a lot of algae, but this is an example of the little bit that we did see. Moving farther north, the ice coverage got a little bit higher, but you can see we're still in pretty thin ice, maybe 20 centimeters at this time. But the ice was quite rough. So here's a couple images of the roughness of the ice. I wasn't part of the Shiva expedition, but I understand, speaking with those who were also on the Fedorov, that the ice roughness for MOSAiC is considerably greater than it was for Shiva, although the ice thickness is considerably thinner. So kind of a dynamic history, I think it's fair to say, for this ice. Here's another example of some of the roughness around Polarstern. You can see for scale a couple of polar bears out in front of the bow of Polarstern. The flow that was chosen, this is an image taken from a helicopter. So we see Polarstern over on the left-hand side. And generally in the foreground of this image is thicker ice, something closer to a meter, though probably not a full meter in most places, but you can see a lot of ridging there. And in particular, this fortress ridge, which is kind of in the middle of the photograph, running left to right, is sort of the main infrastructure ridge for the flow where they're running power lines and such. On the far side of that is thinner ice, much more dynamic over there, and in general, pretty dynamic around Polarstern in general. Some of the main measurement camps are over on the right-hand side, for example, Met City and Ocean City. The L sites and in general, the broader distributed network looks like this. So the L sites being the 3 of them, there are really intensive observations of buoys there. M sites and P sites are lower intensity observations, simpler measurements, and for the triangles, the P sites just GPS. Over on the right-hand side, the schematic from the planning is actually pretty well represented by the map that we ended up with. Polarstern being the star in the center, and then the distributed network around that. So I'll focus briefly in my last three slides, on the L sites, L1, L2, and L3, which again are the more intensive observations. So here's an example from L1. So we're seeing ice mass balance buoy in the foreground, that's Carell's buoy. And then from Naval Postgraduate School, you can see Tim Stanton working on his buoy right in the center there, and over on the right-hand side, I believe that's Ola Person, or perhaps he took the picture and that's myself, at the ASFS, which is the atmosphere buoy. So we deployed these on about 1.7 meters of ice, but pretty complex profile with rafted ice layers and salt water observed in between, about 9 centimeters of snow. At L2, we deployed over a frozen melt pond, not completely melted through, so it's composed of some water in there still, about 8 centimeters of snow on top of the vertical profile that included 2 separate layers of about 30 to 40 centimeters of ice. And then finally, L3, this is the distant node. This one is about 23 kilometers from Polarstern. The other two were about 12 kilometers from Polarstern. This is a thin ice deployment, so we're on a very simple profile, just a flat pan composed of about 30 centimeters of ice. And a little bit less snow, about 6 centimeters on top of that. That's all I have. Thank you.
Great, thank you, Chris. And I think we can take a quick question or two in between, if anybody would like to have any clarification questions or ask Chris about anything concerning the initial deployment philosophy for MOSAiC. Okay, not hearing anything, and if you have a question, you can always type it into chat or save it for the rest of, or towards the end of our other 2 updates. But next we'll hear about ISAT-2 thickness results. And I will stop sharing my screen.
Thanks. And it should be Nathan who has joined the call. Nathan, are you there?
Yep, I'm here. Can you hear me?
Yes.
Okay.
So feel free to share your screen.
Okay, I have to...
It's a green share button at the bottom.
Okay. All right, can you see that?
Yes, and then if you just...
Full screen?
Yeah.
Yeah.
Looks great.
Okay, great, thanks. So I'm here on in partner with the ISAT-2 science team, so the CI science team, Ron Kwok and Sinead Farrell, and I also have Alec Petty here in the room with me as part of the ISAT-2 Project Science Office. And so what we've been developing are products for ISAT-2, including CI's freeboard and converting this to thickness. And so just giving an update on the first data set that's coming out. So ISAT-2 has been up for about 14 months now on orbit. For the most part, the spacecraft has worked very well. We've collected very good data. About the only blip was between June 26th and July 9th. There was a safe hold event, and this was a sensor malfunction rather than anything big breaking on the spacecraft. So we did lose some data from that time period and potentially a bit for a few weeks afterwards that we're still investigating. But for the most part, Atlas, ISAT-2 is very healthy, and all performance metrics are nominal, and so everything's working pretty well on the spacecraft. We had our first public data release on May 28th, and so all the products, or at least most of the products I'm going to be showing here are now publicly available. Some of the data products that are available that are of interest probably to people here would be the geolocated photons. So that's ATLO3. That's just the elevation of each photon. I have an example down here from the nearest strait. But then we have derived products, CICE elevation and freeboard. So these are higher level products that Ron Kwok, as the algorithm lead, has been leading these. And so these are ATLO7, which you can see the link there. That's the height or the elevation of the sea ice retrieved from aggregations of photons, and then ATL10, that's the derived freeboard from that as well. There's other products if people are interested, things like atmospheric products, ocean height, and then also a link to open altimetry. If people are interested in just visualizing data a few passes, it's a really good website for doing that. So next slide. So just what do the data look like? So beyond ATL03, the actual retrieved sea surface height elevation, these are aggregations of 150 photons. And so the data looks something like this. This is a slide from Ron Kwok. One of the important things that we found looking at this data was a height precision. You can see there's a very flat surface. This is a lead. The precision was slightly better than 2 centimeters. And so this is what we are going for to meet our mission requirements to get the accuracy level on sea ice freeboard. Moving to higher level products, ATL10 is sea ice freeboard. And so Ron led a paper that was published in JGR recently. And so we're looking at the aggregations of the freeboard product. So the freeboard product itself is a variable length resolution, somewhere between about 20 to maybe 50, 60 meters, depending on the photon rate that we're getting back from the surface. And then we can aggregate these into grids to get a gridded freeboard data set over the course of the month. And what you can see, as outlined in the paper here, is you can see the growth of the sea ice freeboard being a combination of the ice thickness and snow depth. And you can see, again, the growth of the ice over the course of the year over both first year and multi-year ice regions. And so I'll note that currently ATL10 is a shot-to-shot product. There is a monthly gridded sea ice freeboard product that's under development. It will be distributed at NSIDC after all is checked out in that. One of the main things with gridding the freeboard data is because the length scale is variable resolution, that has to be taken into consideration when you actually aggregate the data and turn it into grids. And that's what's been done here. It's described in the paper, but we will have a forthcoming product that does that already for people. Showing some other work from Sinead Farrell. And this is key because one of the important things to get sea ice thickness from the freeboard is the snow depth. And so what Sinead looked at was the laser and radar freeboard combined, so from different satellites, ISAT-2 and Cryosat-2, as a way to look at the snow depth. And so this was done going back to work that Catherine Giles did 17 years ago, looking at difference between laser and radar freeboard together. And so what Sinead found is looking at the laser radar freeboard differences is that there are some differences with snow depth from the climatology or from what IceBridge radar retrieved, but at least the spatial pattern is mirroring the first year and multi-year ice distributions. So then moving on to sea ice thickness. So this is work that Alec Petty has led. He submitted a paper on this. It's under review currently. So what we've done then is taken the ATL10, the freeboard product, and then combine that with snow depth information, either from the NOAA model, which Alec has also developed, or the Warren climatology, and then convert that into sea ice thickness via the hydrostatic balance equation. And so one of the things that we're getting from this is not just like a gridded sea ice thickness, but the sea ice thickness of each shot from ISAT-2. And this is done by incorporating data from Operation IceBridge, where this is work that I've done where we've looked at the distribution of snow and freeboard over different length scales, and how do we distribute snow from something very low resolution like a model or the climatology onto each ISAT-2 shot to actually retrieve the sea ice thickness distribution and not just the mean value. So we're getting both. And then also, you can see a profile from a 1 kilometer section of multi-year ice data in the Central Arctic. And then you can see the calculated uncertainty there, which does depend on various factors. But this is work that's under review, and depending on how the review process goes, this will be a forthcoming product that will be put out as well. And then one other thing, just showing not just a section, but also just kind of a teaser of different regions. We can see the mean thickness and the distribution. This is from January, from different regions in the Arctic Ocean. And for the most part, the distributions and the means and the shapes do make sense. And also what was looked at here was there's different beams. ICET2 has in total 6 beams. We typically use the 3, they're called the strong beams, where we get, has a higher energy, and we can get a smaller length scale for the aggregation of the photons. And so for the most part, the beams are pretty consistent with each other. So just in summary, ICET2 is very healthy. It's operating pretty well, except for that small blip from safe mode earlier in the year. But again, for the most part, operating quite well. The sea ice height and freeboard products, these are currently available at NSIDC, so people can download these as they wish. The gridded sea ice freeboard product is forthcoming at NSIDC. I don't have an update or a timetable yet, but I don't think this should be too many more months away. Sea ice thickness product, again, this is pending peer review manuscript for when this could be made available. And otherwise on the project, we're really working towards aside from things like CalVal, the data, which is more of a different kind of a presentation. We're also looking just to get the data latency down. So we have a requirement for a 45-day latency on the data. We're not quite there yet, but again, in the coming months, we should get towards that 45-day latency. I have heard a number of people have expressed interest in rapid products for even higher latency. And so we have submitted a proposal to do that, but we haven't heard anything back on that quite yet. But that's where we are with ICET2. Happy to take questions.
Well, it looks like there's a question in the chat. Julie asked what the difference is between the Central Arctic and Inner Arctic on the last map that you showed, I believe.
Let me find that. This one.
Oh yeah, sorry, that is a bit confusing. Sorry, hi, this is Alec. Central Arctic is that kind of blue blob in the middle of the Arctic, and then Inner Arctic is all the peripheral seas, except for the Bering Sea and the Greenland Sea and Baffin Bay. So it's somewhat representative of what other people have used in studies to characterize like an Arctic Ocean region for sea ice studies.
Thank you.
This is Melinda. I have a quick comment. There is a really nice website for looking at the ICET2 freeboard and elevation products. It is openaltimetry.org. I just thought of this, and I think it would be a great way to look at data, just browse through it and see what it looks like, and I'd encourage everyone to check it out.
Yeah, thanks, Melinda. It is very useful, very easy to use. So you have a minute of free time, check it out.
Melinda, will you share that in the chat?
Yes, I will. Thanks.
Nathan, this is Sinead. I think you had that on one of your earlier slides. Is that right? Maybe?
Yeah, it's,
I'll scroll back to that.
Yeah, Sinead suggested I put this in too. So yeah, there it is.
Okay, right at the bottom. Yeah, it's a really nice visualization tool for just looking at the data over the entire Earth, not just sea ice. So pretty cool.
Great. Well, thank you so much. And our next speaker up is Cameron Planck from Dartmouth. So Cameron, if you want to tee up your screen.
Sure. Can you hear me?
Yes.
Okay, good. Let's see. I'm going to do share, and I'm going to do the whole desktop. I need to move this bar. Okay, how's that looking? Can you see the presentation?
We can.
Okay, great. All right, so hi, everybody. My name's, will it work? There we go. My name's Cameron Planck. This is my first IARPIC meeting, so happy to be here. And thank you to Melinda Webster for inviting me. I wasn't quite sure exactly what these presentations looked like or the audience, so I figured I would just give a kind of, all-encompassing start from the beginning. I'm a, I guess, fifth year now graduate student at Dartmouth College in the Thayer School of Engineering. I have a BS in mechanical engineering from Oregon State. I saw some Oregon State people and they joined the group, so shout out to Corvallis. And I worked for Don Perovich and Chris Polashensky. And our focus is improving understanding of the evolution of mass balance of Arctic sea ice. And in principle, or in general, my big focus for my PhD has been developing sea ice mass balance buoys. Or really kind of continuing some of the work that was done down the road from Dartmouth at the Cold Regions Research and Engineering, with Jackie and Don. So through this presentation too, I'll be showing you a few different products, both hardware and software. And a lot of this was developed at Dartmouth at Thayer, but then I also, and I'll kind of get into more detail about this later, but I also started a company a couple years ago to take some of this work and make it more available to the community. So that company is called Cryosphere Innovation, and I'll be kind of talking about everything all as one throughout the presentation. It's a very kind of synergistic thing that we got going. So with that, I'll just introduce, this is a lot of words, I'm sorry. I kind of tried to keep to the 5 to 6 slide cap. Basically, I'll summarize this noisy slide. Our understanding of the Arctic is limited by our ability to observe it. And certain things, the Arctic is obviously best observed basin-wide from above, but certain measurements are really kind of only had locally in situ. And one of those is mass balance, understanding how the ice grows, how the ice melts, whether it melts from the bottom or from the top. So my work here has been creating kind of the 3rd generation product to help us do this, to help us get this measurement. In particular, this buoy that I'm talking about here was designed to be really reliable and low cost. There's a paper written on this that you can find. It's linked at the bottom. So the goal of this presentation really isn't to talk about the details of this instrument, but really to talk about the data that it produces. But a couple of quick facts for you. It's a 16 foot long, 17 foot long with the ballast spar type buoy that floats upright in open water. And it's equipped with 2 ice facing acoustic sounders that allow it to directly determine ice surface and bottom ablation as well as bottom growth. It also has a 192 position vertical temperature string. It's the Brunson string that is kind of ubiquitous across ice mass balance buoys now. And it's designed to be just kind of well-rounded and deployable. So it's lightweight, it's relatively low cost compared to previous instruments, and it's really tried hard to make this, to design this buoy to be as reliable as we could. So moving on, kind of thinking about the data collection problem here. We were sort of initially tasked with creating a buoy, but really what we want is a data collection modality. We want to generate more data, and the way that we kind of tackled that problem is by thinking about it as, SIMB3 is kind of only useful if we have them and if the data that they create is available. So that's kind of what this presentation is about. So without going into too much detail about SIMB3, I'll just tell you that, again, we started Cryosphere Innovation to make them available. So this is a commercial company that produces these. We make them in West Lebanon, New Hampshire. Up to this point, since 2017, we've built 22 of these, supporting 11 international research programs, and in both the Arctic and Antarctic. And we have successfully collected time series data in ice as thin as 10 centimeters. Also, I'll just add that our buoys are designed principally to be deployed and never recovered, but we also have data now from scientists that have used them and then also recovered them and then redeployed them, which is kind of fun. So kind of thinking about the data, we've done a lot of work to try to keep all of our data in a clean, standard form. It's just the data from these instruments is represented as a CSV file with a header, and it's been exactly the same across every SINB3 that's ever been made. So any of the data from these now and into the future will all be the same. It just makes processing easier, obviously. Yeah, at the bottom of this website, you can see a link, and I'm going to click that and bring you over to the website that I made. So Cryosphere Innovation is, I built a dynamic database-driven website to take the data that these buoys present and plot it in real time. So what we have is a 3D globe that plots all of these instruments in real time, along with their drift tracks. Oops, sorry, their drift tracks and the NSIDC near real-time ice concentration. So obviously, MOSAiC's kind of the hot topic right now. So we have 4 instruments located at all of the L sites and at the central polar stern. And you can kind of, it's a little tricky to do here, but you can kind of zoom in and you can see the drift tracks, and you can click on the instruments and view a little kind of blurb about them. But then in particular, you can click on the hot link and it'll take you to the real-time data page. So here you can see data transmitted from the buoys, again, in real time. The MOSAiC buoys transmit at 0, 4, 8, 12, etc. UTC, and the time from transmission to being posted on the website is 10 minutes. So all of this data here, you can see the last time this updated was, it's off. I have it plotting in Eastern Standard Time. It should be UTC, but this is the last transmission was at 11, so it'll transmit again at 3 Eastern Standard Time. These are the reportings from the last transmission. You can also manipulate the buoy here in the on the globe. But then we also plot the time series, so you can come in here and see the air temperature, the barometric pressure, ocean temperature, and the battery voltage, which really isn't pertinent to any researcher, but it's good for our diagnostics. Also, I'll point out on the left, we have a spot for notes and information. So it's actually really interesting to see some of the pictures from Chris's presentation. I've never seen, I built all the buoys on MOSAiC, but I've never seen any pictures of them deployed, so that was pretty cool. But I'm still waiting on the report from the ice conditions. The data can also be downloaded here in the upper right. But then again, kind of looking at these plots, these are all interactive. You can click, you can zoom, and then you can export these all as PNGs. And then we also have the mass balance here. So this is the ocean below, the ice in the middle, and the snow position on the top. And you can see that this is completely unfiltered data. This is hot off the instrument. There's a little bit of noise here in the center. We believe that that's due to snowstorms, unconfirmed. But in general, our instruments are pretty good. They're not super noisy, which we're happy to see. So that's the bulk of the website. I'm going to flip back to the PowerPoint, and I actually wasn't sure when I was putting this presentation together. I wasn't sure if I would be able to screen with you. So this here, this page really just rehashes everything I just said in terms of MOSAiC and what our page is capable of. So I'll just go ahead and skip that. This is my last slide. I just want to kind of leave you with a couple of notes. So everything on our database, everything on our data page is database driven, and therefore it's in a MySQL database. So it's all available programmatically in Python, C, and I imagine Fortran. somehow. And also, any of the plots on the website can easily be embedded into any website you ever choose to, in just one line of code. So that's kind of nice. They've kind of specifically designed it that way. And then lastly, I'll just note that cryosphere innovation is, and a lot of the work that I've just presented is sort of work that I do in addition to being a PhD student. So development is sometimes kind of slow, but I do actively develop both the hardware and the software. And I'm always looking for ways to make our product more useful to researchers. So if you ever have any questions or any comments on anything related to SINB3 or our website, or if you have specific features that you would like us to work on implementing, please let me know. And my contact information is right here on the last slide. And that's it.
Well, thank you so much, Cameron. That's really, really amazing information, especially because as you said, you haven't seen a picture of your instrument deployed at MOSAiC, and I haven't seen the really nice data portal you've created for MOSAiC. So I appreciate that, and I'm sure a lot of other people do as well. So let's put it, we have about 10 minutes for open discussion for any other questions you may have come up with after you've just heard our three speakers. And so we'll put it to the floor for anybody to participate at this point.
Cameron, I have a question about your buoy. How do you tell the snow from the ice?
That's a great question. We rely on the initial conditions. So in fact, basically what we do, the deployment process looks like this. You drill a hole in the ice, and then you stand the buoy vertical and you drop it in. And we know pretty much very closely where the buoy floats to. And it instantly, not instantly, it eventually freezes in and it becomes sort of this fixed reference frame. So with the initial conditions of ice thickness and snow thickness and then a fixed reference frame, we can distinguish snow from ice.
And that's using temperatures, or do you have like a density measurement device of some sort in the
Yeah, so we have a high resolution digital temperature string that measures temperature from the air through the snow into the ice and into the ocean at 2 centimeter intervals. So we have very, very nice temperature profiles, especially in the thermodynamic interfaces of ice and snow, air and snow, etc., are very visible when it's cold. But we also, kind of what makes our buoys different is we use acoustic rangefinders that directly measure the distance from the fixed reference frame to the surface and bottom position.
And Cameron, presumably during MOSAiC, you have a host of ancillary other observations within probably walking distance, and hopefully nobody's walking there, but you have a sense of atmospheric conditions as well from the other sensors that at least I saw in that picture.
Yeah, absolutely. Our buoys, kind of only give you one data point, in terms of understanding the oceanic and atmospheric fluxes. So any co-located instruments allows us to do much better science, and that's generally how we try to deploy these. MOSAiC is an intense case where we have lots of instruments, but even when we deploy in the Beaufort, for instance, or elsewhere, we try to always have a series of instruments.
Can I ask a quick question?
Sure.
Yeah. How much do they cost, and how easy are they to install? I don't know if you already answered those things.
Yeah. So they cost $15,000, and they take about 25 minutes to install, depending on how hard it is, depending on what kind of equipment you have to drill the hole in the ice. They're they're installed completely in about 3 steps. There's no electrical connections that have to be made, and there's no tools that are required. You simply take the 2 halves of the buoy and couple them together, and then you flip one switch, and there's a blue light that turns on. The blue light turns off as soon as the instrument connects to iridium and successfully transmits. Once it does that, it's ready to be deployed, and you just stand it up and drop it in, and then you can go home.
What is the power source for it that lasts so long?
Great question. There's an 18-volt battery located in the bottom section. It's 60 D-cell batteries arranged in a way that gives us basically 5 stacks of 12 batteries in series. And that gives us an operational lifespan of about 2 years by power budget. And we specifically use alkaline cells to avoid any kind of shipping issues with lithium batteries.
Mm-hmm.
Cameron, it's Martin Jeffries at CREL. Following up on the question about the cost of the buoys, I wondered about the web support. Is that something you created just for the buoys deployed at MOSAiC, or is that a service that's included in the purchase price of every buoy?
So that's a service that I just kind of created in my free time, actually. I really enjoy doing that kind of work. But it's now that the infrastructure is there, it's trivial to add other instruments. So no, it's not just MOSAiC. And in fact, if you go to the website, you'll notice that on the globe there will be let's see, 2 other instruments. One located in the Beaufort currently operating, another located in the Southern Ocean by Antarctica. Those are both completely separate projects. And then also there are archived results from other buoys that have been deployed and retired. And those results, while not plotted on the globe, are available on the website as well.
Great, thank you very much.
You're welcome.
Hey, this is Hayo Aiken with a question.
Hi.
This is great. Good to see this move forward. My question kind of builds on Martin's, and that is, what do you see? Do you have a vision, or have you talked with some of your collaborators as to what the longer term perspective on sharing and archiving buoy data is? Right now, it's kind of whoever purchases a buoy ultimately is responsible for long-term archival. What you've laid out here is a great approach to make the data accessible in near real time and sort of in a bit more of a context. But is there, in terms of the approach that, say, the International Arctic Buoy Program is taking, where they're having their buoys report into global networks like GTS and others? I mean, do you see something similar for the data that you're generating? And if so, what is it that the research community or programs like Global Cryosphere Watch, CryoNet, and others could do to help move things along?
Yeah, well, that's a great question. It's been kind of interesting. I started this program. Well, this is a continuation of a program that obviously was developed at CREL and then sort of slowly transferred to Dartmouth. And this is a result. You guys are all, I'm sure, familiar with Jackie's work and Chris Bolashensky's work developing the first IMB, and then of course Don developing the first IMB and SIMB. What's been really fun about kind of taking some of this more commercial is I've had the opportunity to work with researchers all over the world. And in general, what I found that's been really cool to see is pretty much everybody wants their data available. And so that's, obviously there are some ownership issues with just hosting a whole bunch of data on a website here. But in particular with MOSAiC, that's in the grant that, that everything needs to be available and as fast as you possibly can. And in addition, some of the work I've done with collaborators at McGill University, it's the same thing that's in their grant as well. In fact, I've only had one person not want me to host their data. And I've actually sold one of these to an oil company, even, well, an energy company technically, that was more than willing to share their data. So that's interesting. So our Cryosphere Innovation website is kind of becoming a hub where we have a lot of this data, but also what's kind of cool now is that I have this whole backend built out in Python that allows me to kind of manipulate and move this data wherever we want. So one step that you know, I'm sure we'll end up tackling in the future here soon is piping this data to other areas where that maybe are a little bit more well-known or more established. That's something I think I can do like pretty easily.
Thanks, Cameron. If I can just quickly comment on that, that's good to hear. I would encourage you, you know, we have the Arctic Observing Summit coming up in late March, early April of next year in Akureyri, where those types of questions, how do we better bring these different data collection observing approaches together, are going to be discussed. It might be worthwhile for you, if you haven't already, considering submitting a brief white paper. Contact me about that directly. You know, we can extend the deadline for a few folks, and I think this is a really important topic where more progress could be made if you can tie this to sort of these longer term sustained operational programs like GCW or CryoNet.
Absolutely. I'd love to do that.
Thanks.
Mm-hmm.
Well, I think we have time for one more question, and
if anybody, like I said, kind of in the cloud here on the page, if anybody has any ideas for processes or features that they'd like to see developed, especially in our hardware, let me know. I can kind of think at any one time of a million different things I could change or add to the SINB, and I just have to basically, you know, assign engineering time to them. It's kind of, some of them are kind of arbitrary to me. You know, I can spend time doing anything. So if you have any strong feelings, let me know.
I have a question about the ISAT-2 talk. I was just wondering, can you say something about what drives the latency of, say, greater than 45 days in terms of getting products out? So in other words, how far are we from ever getting to something like 4 days of latency?
Sure. All right. So right now, what's driving our latency for what are called final products are we have to get our infrastructure for getting orbits set up, and then for data review. And so it takes, I think, 2 to 3 weeks or so to get the best solutions for the orbits to come out. So that's primarily what's driving us right now. We do have what are called rapid products that we could make available. The orbits aren't as good, I think, for getting things like CIRES freeboard, because the errors that come into the orbits aren't so important there. I think we can get a good CIRES freeboard product, but there it's a question of getting infrastructure set up for things like doing a rapid product and then getting that shared rapidly. So I think it's doable. It's just, again, people's time, programming. There are additional errors that come into doing things faster, but yeah, proposals are in to do this because I think people do see the importance of it, and we'll try to get it moving forward.
Thank you.
well, thank you, everybody. I know we've hit noon Mountain Time, and I would just like to say that I think this has been such a great meeting, and even though I've been so close to one of the topics, I learned a lot even from the presentation. So thank you to all the presenters. And I will bounce it back to Meredith to close us out. And over to you, Meredith.
Thank you, Janet. just one quick note. Josh asks if there's a website or streaming capabilities for the NGA Domain Awareness Conference. If anyone has information on that, you can speak up or type it in the chat before we close. And as far as I'm aware, because of AGU in December, the CIRES collaboration team will not have a December meeting like in the context of these webinars. But as you heard, there's lots of activities happening at AGU. And sorry, I'm pulling up the spreadsheet to see what the next topic is for CIRES. And I don't think we have it planned out yet. So stay tuned for that. Okay. Thank you, everyone.
Thank you all.
Thank you.
Bye.
Thank you.
Thank you.